Good morning everyone. My name is Froilan Villanueva. Together with Miss Dines Lupon Salan, our topic for today is all about pumping lemma context, pre-language or CFL. Pumping lemma. So what is pumping lemma? In computer science, in particular in formal language theory, the pumping lemma for context-free languages, also known as the Bar-Helen lemma, is a lemma that gives a property shared by all context-free languages and generalizes the pumping lemma for regular languages. The pumping lemma can be used to construct a proof by contradiction that a specific language is not context-free. Conversely, the pumping lemma does not suffice to guarantee that a language is context-free. There are other necessary conditions, such as Ogden's lemma or the interchange lemma. Pumping lemma is used to check whether a grammar is context-free or not. Properties of context-free languages. Union. If language 1 and if language 2 are two context-free languages, their union L1, union L2 will also be context-free. For example, language 1, A power n, B power n, C power m, where m is greater than or equal to 0 and n is greater than or equal to 0, and language 2 is equal to A power n, B power m, C power m, where n is greater than or equal to 0 and m is greater than or equal to 0. Language 3 is equal to L1 union L2 is equal to A power n, B power n, C power m, union A power n, B power m, C power m, where n is greater than or equal to 0. M greater than or equal to 0 is also context-free. Union. Language 1 says number of A's should be equal to number of B's, and language 2 says number of B's should be equal to number of C's. Their union says either of two conditions to be true. So, it is also context-free language. CFL are closed under union. Concatenation. If language 1 and if language 2 are two context-free languages, their concatenation, language 1 that language 2 will also be context-free. For example, language 1 is equal to A power n, B power n, where n is greater than or equal to 0, and language 2 is equal to C power m, D power m, where m is greater than or equal to 0. Language 3 is equal to L1 that L2 is equal to A power n, B power n, C power m, D power m, where m is greater than is equal to 0 and n is greater than or equal to 0 is also context-free. Clean closure. If language 1 is context-free, its clean closure language 1 times will also be context-free. For example, language 1 is equal to A power n, B power n, where n is greater than or equal to 0. Language 1 asterisk or times is equal to A power n, B power n, where n is greater than or equal to 0, times or asterisk is also context-free. Note, so CFR are closed under the clean closure. Intersection and complementation. If language 1 and if language 2 are two context-free languages, their intersection language 1, intersection language 2 need not be context-free. For example, language 1 is equal to A power n, B power n, C power n, where n is greater than or equal to 0 and m is greater than or equal to 0, and language 2 is equal to A power m, B power n, C power n, where n is greater than or equal to 0 and m is greater than or equal to 0. Language 3 is equal to L1 intersect L2 is equal to A power n, B power n, C power n, where n is greater than or equal to 0, need not be context free. Intersection and complementation. Language 1 says number of A's should be equal to the number of B's, and language 2 says number of B's should be equal to the number of C's. Their intersection say both Both conditions need to be true, but push down automata can compare only two. So, it cannot be accepted by push down automata, hence not context-free. Similarity, complementation of context-free language 1, which is there exists times minus language 1, need not be context-free. CFL are not close under intersection and complementation. Pumping lemma for CFL states that for any context-free language, it is possible to find two substrings that can be pumped any number of times and still be in the same language. For any language L, we break its string into 5 parts and pump second and fourth substring. Pumping lemma here also is used as a tool to prove that a language is not CFL. Because if any one string does not satisfy its conditions, then the language is not CFL. Pumping lemma CFL statement, for every context-free language L, there is an integer n such that for every string z in language of length greater than n, there exists z is equal to ubwxy such that length bwx less than n and the length of bx greater than 0. For all I greater than 0, ub power of I, Wx power of I, Y is in language. Application of lemma. Problem. Find out whether the language L is equal to x power n, y power n, z power n, where n is greater than or equal to 1 is context-free or not. Solution. So, let L is context-free, then language must satisfy pumping lemma. At first, choose a number n of the pumping lemma, then take z as 0 power n, 1 power n, 2 power n. Application of lemma. Break z into ubwxy where length bwx is less than or equal to n and bx is not equal or exists. Hence, bwx cannot involve both zeros and twos since the last zero and the first two are at least n plus 1 positions apart. There are two cases. Case 1, bwx has number 2's, then bx has only zeros and 1's, then uw y, which would have to be n, L, has n 2's but fewer than n zeros or 1's. Case 2, bwx has no zeros. Here contradiction occur. Hence, L is not a context-free language. Pumping lemma CFL example. For example, 0 power n, 1 power n is CFL, as any string can be the result of pumping at two places, one for 0 and other for 1. Let us prove language over 0, 1, 2 is equal to 0 power n, 1 power n, 2 power n, where n is greater than or equal to 0 is not context-free. Let us assume that L is context-free. Then by pumping lemma, the above given rules follow. We should that for all u, v, w, x, y, 1 minus 3 do not hold. Now, let x, L, and length x greater than or equal n. So by pumping lemma, there exists u, v, w, x, y such that 1 minus 3 hold. We show that for all u, v, w, x, y, 1 minus 3 do not hold. If 1 and 2 hold, then x is equal to 0 power n, 1 power n, 2 power n is equal to u, v, w, x, y with length bwx less than or equal to n and length bx is greater than or equal to or greater than or not equal to 1. 1 tells us that bwx does not contain both 0 and either bwx has number zeros or bwx has number 2's. Thus, we have two cases to consider. Suppose bwx has number zeros by 2, bx contains a 1 or a 2. uwy has n zeros and uwy either has less than n ones or has less than n twos. But 3 tell us that uwy is equal to b power 0, wz power 0, y, there exists language. So uwy has an equal number of zeros, ones, and 2 gives us a contradiction. The case where BWX has no twos is similar and also gives us a contradiction. Thus, language is not context-free. So, we have here example of videos how pumping lemma explained. That's all.
In this lecture, we'll be studying about pumping lemma for context-free languages. So what is a pumping lemma for context-free languages? Pumping lemma for context-free language is used to prove that a language is not context-free. So if you remember, we have already studied about pumping lemma for regular languages, where we use the pumping lemma to prove that a given language is not regular. So if you have not watched that video and if you need to study about that, you can watch it in this playlist. And if you have already watched it and if you have already studied it, then this pumping lemma for context-free languages should not be a difficult topic for you, because the pumping lemma for context-free languages is almost similar with that of the pumping lemma for regular languages, but yes, there are a few differences. So we shall see what they are, and we shall see how we can use this pumping lemma to prove that a language is not context-free. Alright, so let's see how we can do it. If A is a context-free language, then A has a pumping length P such that any string S where the length of S is greater than or equal to P may be divided into 5 pieces S equal to U, V, X, Y, and Z, such that the following conditions must be true. So what we do is, let's say that we have a language called A. So we say that if A is a context-free language, then A will have a pumping length P. So we don't know what is the pumping length P, but it will have some pumping length such that any string S, so S is a string from this language A, where the length of S is greater than or equal to the pumping length P, that string S can be divided into 5 pieces such that S equal to U, V, X, Y, and Z. So if you remember, when we studied for pumping lemma for regular languages, we divided the string into 3 pieces. But in this pumping lemma for context-free language, we will divide the string into 5 pieces, U, V, X, Y, and Z, such that the following conditions must be true. So if you divide it into 5 pieces like this, these 3 conditions must be true. And what are they? U, V raised to I, X, Y raised to I, Z is in A for every I greater than or equal to 0. So you have divided S into U, V, X, Y, and Z, and here if you raise V to the power of I and Y to the power of I, where I is greater than or equal to 0, then the string that you get even after doing this should also be in A. That means that string also should belong to the language A. And the second condition says that the length of V and Y should be greater than 0. And then the third condition says that the length of V, X, and Y should be less than or equal to P, which is our pumping length. So remember that these U, V, X, Y, Z, they are not strings, but they are the parts into which you have divided the string S. And after you divide this, these 3 conditions must be true. And if these 3 conditions are true, then we can say that it is a context-free language. So we are going to prove that a language is not context-free using this pumping lemma. So this is the conditions that we know, and let's see how we can prove it using pumping lemma. So in order to prove that a language is not context-free using pumping lemma for context-free languages, we have to follow the steps that are given below. So just as we did in the case of pumping lemma for regular languages, even in this case, we will prove it using contradiction. Alright, so here we have the 3 conditions given and we already defined them. And now, since we are going to prove it using contradiction, what we will do is we will assume that A is context-free. So we have a language that we call A, and we will assume that it is context-free for the beginning. So we have already read that if a language is context-free, then it has to have a pumping length, and let's call it P. So as we assumed A is context-free, so it should have a pumping length, which we will call P. And then all the strings longer than P can be pumped. So any string whose length is greater than or equal to P can be pumped. That's what we read above. Now what we will do is we will find the string S in A such that the length of S is greater than or equal to P. So we have our language A, and from this language A, we will take a string which we will call S such that the length of this string S should be greater than or equal to P, which is our pumping length. Now after you take that string S, we will divide that S into 5 parts: U, V, X, Y, and Z. So we have a string and it is divided into 5 parts now. Now we will show that U, V raised to I, X, Y raised to I, Z does not belong to A for some value of I. So you have divided this S into these many parts. So when it is divided in this way, it is lying in this language A. We know that. Now we will show that this string S, which you have divided into these 5 parts, this part of V and this part of Y, when you raise it to some power of I, that means if you repeat this V part and Y part some I number of times, this new string that you obtain, you have to show that it does not belong to the language A. So we don't know what is the language right now, but when you have the example, you will know some rules that have to be followed for the language. So once you divide it in this way and raise it to these powers, you have to show that it does not belong to this language A. After that, consider the ways that S can be divided into U, V, X, Y, and Z. So this string S, when you divide it into U, V, X, Y, and Z, there are many ways in which you can divide it into these 5 parts. So consider all the ways in which you can divide the string S into these 5 parts, and after you find them out, show that none of these can satisfy all the 3 pumping conditions at the same time. So what are the 3 pumping conditions? These 3 conditions that we have read over here. So once you find all the ways in which S can be divided into these 5 parts, show that those divided parts cannot satisfy these 3 conditions of pumping lemma at the same time. So since it cannot satisfy all the 3 pumping conditions at the same time, S cannot be pumped, which is a contradiction to our assumption that A is a context-free language. If A is a context-free language, then it should be able to be pumped. But since we find that it cannot be pumped, we get a contradiction. Thus, we prove that A is not a context-free language. So these are the steps that you have to follow in order to prove that a given language is not context-free using the pumping lemma for context-free languages. So don't worry even if you feel a little bit confused seeing all these rules and steps. In the next lecture, we will be taking an example in which we will clearly see how to perform these steps in order to prove that a given language is not context-free using the pumping lemma for context-free languages. So thank you for watching this, and see you in the next lecture with an example which will clarify this further. In the last lecture, we have studied about pumping lemma for context-free languages, and in this lecture, we will be taking an example to see and figure out how the pumping lemma for context-free languages actually works. So here we have an example language given, L equal to A power n, B power n, C power n, where n is greater than or equal to 0. So the meaning of this language is that we can have symbols of the form A, B, C, and then the number of A's should be equal to the number of B's, and it also should be equal to the number of C's. That means if you have n number of A's, you should also have n number of B's and also n number of C's. So it means the number of A, B, and C should always be the same. That is the rule of this language that we have. So our task is to show that this language is not context-free, and we will do this using pumping lemma for context-free languages. So let's see what are the steps that we need to follow. So the first step is we will assume that the language L is context-free. And why are we doing this? We studied in the previous lecture that the way we are going to prove this is using contradiction. So first we will assume that L is context-free, and we will show that there is a contradiction to our assumption, and hence it is not context-free. So we'll see how we do that. So first we have this language L and we assume that it is context-free. So if it is context-free, then the language L must have a pumping length. This also we studied, and we will call the pumping length P. And now we will take a string S such that S is equal to A power P, B power P, and C power P, where P is our pumping length. And then we have to divide S into 5 parts U, V, X, Y, and Z. So let us just look at the rules of this pumping lemma that we studied in the previous lecture, just to recall those. So this is the rule of pumping lemma that we studied in the previous lecture. And we said that if a language is context-free, then it will have a pumping length. So we already assumed that our language is context-free. So it will have a pumping length P. And then we have to divide our language into 5 pieces, U, V, X, Y, and Z, which we will do. And after dividing that, you have to show that U, V raised to I, X, Y raised to I, Z also belongs to the same language for every I greater than 0. So this condition must hold if the language is context-free. And also condition 2 and 3 must hold. So we will focus on condition number 1. So let's go back to our problem. So here we have taken P as our pumping length, and we are going to divide our string S into 5 parts, U, V, X, Y, and Z. So let's see how we can do this. So here, for example, I have taken the pumping length P is equal to 4. You can take any other length also, but here, for example, we have taken our pumping length P, which is equal to 4. And so we have the string A power P, B power P, C power P. So all the P's I replace it with 4. So I have my string of the form A power 4, B power 4, and C power 4. So this is the string that we have, and our next step is to divide the string S into parts U, V, X, Y, and Z. So let's see how we can divide it. There are two cases. Case number 1. V and Y each contains only one type of symbol. So what do I mean by this? I'll show you. So here I've taken this string A 4 times, B 4 times, and C 4 times. So this is the string that we have. Now I'm going to divide it into U, V, X, Y, and Z such that V and Y each contains only one type of symbol. So let's see. I will take these two A's. This part will be my V. And then I will take this C over here, just this one C, and this will be my Y part. So what will be the remaining one? This A over here, this is my U, and this A, B, 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 and up to this C, this is my X, and this two C's over here, this is my Z. So I have divided my string into U, V, X, Y, and Z. And the case that we had was that V and Y each contains only one type of symbol. So where is my V? This is my V, and V contains only A, the same kind of symbols. And what about Y? Y also contains only one kind of symbol, which is C. So each V and Y, it contains only one type of symbols. So that is one case or one way in which you can divide it into parts U, V, X, Y, and Z. Now after we have divided, we said that the condition number 1 was saying that U, V raised to I, X, Y raised to I, Z must also belong to the language. So here I have I over here, and I am going to take I is equal to 2, for example. So if I take I equal to 2, that means it will be U, V square, X, Y square, and Z. Now let me replace it here and see what is the kind of string that I am going to get. So if I do this, U, what is my U? U is just 1A. And what is my V? V contains 2 A's. But it is V square, so I have to double it. That means there will be 4 A's. A, 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 A. Then X. What is my X? A, B, 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 C. A, B, 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 C. And then I have y square. What is my y? Y is just one C, but since it is square, I have to double it. So there will be two C's. And then Z. Z contains two C's over here. C, C. Alright, so this is the string that we get. Now let me count how many A's are there. 1, 2, 3, 4, 5, 6. There are 6 number of A's and how many B's? 1, 2, 3, 4. 4 number of B's and 1, 2, 3, 4, 5. 5 number of C's. So this is the string that I am getting. So here I see that A is 6, B is 4 and C is 5. The number of A's is not equal to the number of B's and that is also not equal to the number of C's. So the rule of our language said that the number of A's, B's and C's should always be the same. But when I divided my string into U, V, X, Y and Z, and when I raised this V and Y to the power of 2, the string that I am getting does not belong to the language L, because the resultant string that I get here has different number of A's, B's and C's. So this does not belong to the language L. So this shows that condition number 1 cannot be satisfied. So since condition number 1 cannot be satisfied, we see that our assumption which said that L is context free does not hold. It is a contradiction to our assumption. If L was supposed to be context free, then the string that I get here should also belong to the language L, but it is not belonging to the language L when I do this. So our condition number 1 itself fails. If you want, you can check conditions number 2 and 3 also, but since 1 already failed, so there is no point in actually checking 2 and 3. So from condition number 1 itself, we found that it is a contradiction to our assumption which said that L is context free. So we can say that L is not a context free language from case number 1. Now we can have another case. Let's see what that is. Okay, the case number 2 says that either V or Y has more than one kind of symbols. So this is my string, 4 number of A's, 4 number of B's, 4 number of C's. Now I'm going to divide it into 5 pieces, U, V, X, Y and Z, such that either the part V or the part Y has more than one kind of symbols. So let me see how I can do this. So here, this one, the 2 A's from here and the 2 B's from here, this will be my V. And then this B over here, this will be my Y. So why am I concentrating mostly on the V and the Y part? Because these are the two parts which we are going to raise them to powers. So that is why I am focusing mainly on V and Y. So either V or Y has more than one kind of symbols. This is my V, and in my V, it contains both A's and B's. There are two kinds of symbols. There are more than one kind of symbols. And Y contains only one B, that is fine. So here, this is the condition where at least one of the part among V or Y should contain more than one kind of symbols, which is this one, where V contains more than one kind of symbols, A and B. Now, what will be the remaining part? This will be my U. This is U, V, and this B over here, this will be my X, and the remaining part, this C's will be my Z. Now, let us see if we raise them to the power, what will happen? U, V raised to I, X, Y raised to I, Z, and again I will take I is equal to 2. So this also you can vary it, you can take some other numbers also, but I'm just taking the example of 2. So here let's see, U, V square, X, Y square, Z, because the value of I is 2. Now let's see what will happen. What is my U? U contains two A's, A, and V square. What is my V? V contains A, B, but it is squared, so I have to write this 2 times, A, B, B, and again A, B. And then X, what is my X? It is just B, and Y square. What is Y? Y contains just one B, but since it is square, I have to write it twice. And Z contains 4 number of C's, 1, 2, 3, 4. So here, this is the string I am getting. And what is the pattern of this string? There are A's followed by 2 B's, and again A is repeating, and then again we have some number of B's, and some number of C's. But the language that we had, the L that we had, should be of the form a power n, b power n, c power n. This should be the pattern that should be followed. You should first have n number of a's, followed by n number of b's and n number of c's. But here, after you have a's, you have b, and again you are having a's. So this pattern is not being followed. So we can say that this string also does not belong to the language L. So even when you divide it in this way, taking this case into consideration, the resultant string that you get does not belong to our language L. So since this does not belong to our language L, our condition number 1, it fails. And since the condition number 1 fails, there is no point in checking condition number 2 and 3. If you want, you can check it, but since 1 itself fails, it is a contradiction to our assumption that L is a context-free language. So since it fails, we can say that our assumption that L is a context-free language does not hold, and hence this language L is not context-free. So this is the way, using pumping lemma for context-free language, you can prove that a given language is not context-free. So I hope this was helpful to you. Thank you for watching, and see you in the next one.